Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
We thought we understood Uranus, until we realized we were only seeing snapshots. We've only seen Uranus for about 6 hours, and somehow we've spent nearly 40 years trying to explain it. Sounds like a joke, but it isn't. And those 6 hours? That's all we got from Voyager 2's close flyby in 1986. The entire close-up dataset of an entire planet. 6 hours is nothing, you can't even get through a full airport security line that fast. And yet, from that tiny window, scientists built decades of textbooks, models, and assumptions. So the real question is obvious. How do you go from a 6-hour glimpse to definitive conclusions? Why did a world we barely saw get labeled as quiet, boring, almost inactive? And more importantly, what if we simply looked at it the wrong way? If that's true, then what is Uranus really like? Behind this sit 3 puzzles that still bother planetary science today. First, why is it tilted on its side, basically rolling through space? Second, why does its magnetic field look like someone twisted it out of alignment? And third, why does it seem to leak almost no internal heat? None of these feel like small measurement errors, they feel like structural anomalies. And strangely enough, the first strong evidence for all of this came from those same 6 hours. But the story starts much earlier. In 1781, William Herschel was scanning the night sky with a homemade telescope. He wasn't trying to change history, he was just looking at stars. Then he noticed something odd. A faint point of light that didn't behave like the others. It wasn't fixed like a star. It wasn't a comet with a glowing tail. It moved. Slowly. So slowly it didn't feel like an object at all, more like time itself shifting position. At first, Herschel thought it was a comet. That made sense back then. The solar system was still a simple map, a few planets, the sun, and the occasional comet passing through like a visitor. No one expected the map to grow. But once its orbit was calculated, things stopped making sense. It was too stable, too regular, too clean. Not a comet, a planet. For the first time, the solar system expanded. And yet, there was an uncomfortable twist. This new planet had actually been there all along. It had likely appeared many times in plain sight throughout history. We just didn't recognize it. That leads to a slightly embarrassing truth. It wasn't newly discovered. It was just ignored for a very long time. And in true human fashion, even its naming became a debate. The British preferred Herschel. After the discoverer, the international community leaned toward Uranus, from the Greek sky god. In the end, Uranus won. It sounds formal today, but it almost feels like history quietly saying, let's go with mythology and move on. But the real question isn't the name. It's why it took until 1781 to notice it at all. And the answer is less mysterious than you'd think, but more counterintuitive. First, it's dim right at the edge of human vision. Second, it moves incredibly slowly. Not like Mars, which clearly walks across the sky. Third, it looks ordinary. No dramatic colors. No obvious behavior. It doesn't demand attention. It blends in. So a classic mistake happened in human observation. We saw it, but didn't recognize it. In other words, it wasn't discovered late. It was overlooked for a very long time. And that's the part that gets interesting, because even today, some of what we think we know about Uranus might still come from the same problem. We've seen it, but we haven't fully understood it yet. And that misunderstanding is only just beginning to unfold. After that, things start to feel slightly off. Not because Uranus is chaotic, but because the more we look at it, the less everything seems to fit together. Its most famous feature is its axial tilt, 97.7 degrees. It sounds like just a number, but in reality, it means something wild. Uranus is basically rolling around the sun on its side. Not like Earth, calmly spinning upright, more like a giant planet that got knocked over and just kept moving. And this isn't a small object we're talking about. Q could fit 63 Earths inside it. So this isn't a gentle wobble. It's a planetary scale slow motion roll. It takes 84 years to complete one orbit. That means if you were born under sunlight on one hemisphere, you might spend your entire life in daylight. And night might arrive, for your descendants. The seasons go even further. Each pole gets about 42 years of daylight, then 42 years of darkness. On Earth, seasons are a rhythm. On Uranus, seasons are history unfolding. It's like pressing play on a movie so long that entire generations of directors come and go before the scene changes. And strangely enough, this tilt doesn't just reshape time, it reshapes weather. On the surface, Uranus looks calm, blue-green, almost peaceful. But infrared data tells a different story. Winds can exceed 900 kilometers per hour. That's several times stronger than the most violent hurricanes on Earth. We just don't see it, because methane absorbs the red light, giving it that calm blue appearance. It's a bit like someone standing still in a suit after running a marathon. You assume they're fine, but you're only seeing the surface. So the question becomes obvious: why is it like this? The leading idea is a giant impact. Early in the solar system, a planet-sized object may have slammed into Uranus and literally knocked it sideways. But here's the problem. A collision that big should leave clear structural scars. And the data doesn't fully agree with that idea. So another model appears: multiple impacts over time. Not one accident, but many smaller hits gradually tipping it over. Still, that struggles to explain how the tilt became so extreme and precise. Then there's orbital resonance chaos, giant planets subtly reshaping each other's orbits in the early solar system, slowly pushing Uranus out of balance. But all these explanations share the same pattern. They sound reasonable, but none are fully proven. In other words, we know it's tilted. We just don't know why. We don't even know if it was a single accident or a long evolutionary process. Then came the first real close-up. In 1986, Voyager 2 flew past Uranus. Closest approach, about 81,000 kilometers. Sounds close. But in planetary terms, it's just a flyby glance. And it only had 6 hours. 6 hours. Less than a feature-length movie. And yet that brief moment shaped decades of scientific understanding. What it saw looked quiet. No obvious storm systems. No strong internal heat signatures. A strangely stable atmosphere. From that, a familiar image was born: a cold, quiet, almost inactive ice giant. But here's the catch. That snapshot came from an extremely short window. And even more importantly, the space environment at the time wasn't normal. Later studies suggested the solar wind was unusually strong during the flyby. Uranus' magnetosphere was heavily compressed, meaning what Voyager saw may not have been its true state at all. It was more like photographing a lake during a storm and concluding the lake is always rough, when in reality, it might just have been windblown for a moment. And later infrared and telescope data began to hint at something different. Uranus isn't static. It just changes so slowly that, from our point of view, it looks frozen in place. If the last chapter was about why Uranus is tilted on its side, then this one goes a step deeper. It's no longer asking what it looks like. It's asking something more uncomfortable. If you could actually fall into Uranus, would it even resemble a planet as we imagine it? Let's start with the name we give it: an ice giant. Sounds simple. Cold. Almost like a frozen world floating in space. But that label is misleading. It's not an ice ball. Not even close. It's a high-pressure, high-energy system that behaves in ways that break intuition. Uranus belongs to the giant planet family, along with Jupiter and Saturn. But it's the odd one out. Jupiter and Saturn are mostly hydrogen and helium, huge gas envelopes. Uranus and Neptune are called ice giants, but that ice is not ice in the everyday sense. Not something you can skate on. Not even solid in the normal meaning. If you could somehow fall inward, you'd pass through layers. First, a hydrogen-helium atmosphere, calm looking from a distance, but driven by extreme winds and storms. Then you reach a deeper region made of water, ammonia, and methane under enormous pressure. This is where the term ice giant comes from, but there is no real ice here. Under these conditions, matter enters a strange phase: supercritical fluid. Neither liquid nor gas. Something in between. Dense like a liquid, flowing like a gas. No clear boundaries. No stable shapes. Just a continuous, shifting medium like a planet-sized ocean that refuses to decide what it is. And it exists under pressures and temperatures far beyond anything we can reproduce for long on Earth. Then deeper still, there may be a rocky and metallic core. Small, but incredibly dense. Pressures there reach millions of atmospheres. Temperatures climb into the thousands. At that point, the word ice giant almost stops meaning anything at all. As the saying goes, the deeper you go, the stranger it gets. But the real question is what this structure actually implies. For a long time, models suggested Uranus barely emits internal heat. Unlike Jupiter, it doesn't seem to glow from within. It looks like a cold, inactive world. But that has always been suspicious. Because its neighbor Neptune, farther away from the Sun, radiates clear internal heat. That doesn't quite add up. So newer thinking suggests a different idea. Maybe Uranus isn't cold. Maybe the heat is trapped. Inside, the structure may be strongly layered, preventing convection. Heat cannot rise efficiently. It gets locked in, like a thermos that's too well sealed. Hot inside, cold outside. If that's true, then the picture flips completely. What we thought was a dead planet might actually be a planet that cannot release its energy. And then the story gets even more interesting because heat and structure connect directly to the magnetic field. During Voyager 2's flyby in 1986, scientists found something extremely unusual. Uranus' magnetic field is heavily misaligned. The magnetic axis is tilted about 59 degrees away from its rotation axis. That alone is already strange. Most planets are roughly aligned. Even Earth is mostly stable in that sense. But Uranus looks twisted. And it gets stranger. The magnetic field is not centered inside the planet. It is offset, shifted away from the geometric center. That creates a highly asymmetric magnetosphere, one side compressed, the other stretched, like a bubble squeezed out of shape. At the time, explanations focused on complex internal dynamos or unusual fluid layers. But none of them fully stabilized the picture. So another idea emerged. Maybe the issue isn't only inside the planet. Maybe it's also timing. What Voyager saw could have been a snapshot distorted by external conditions. Later studies suggested that solar wind activity was unusually strong during the flyby. That could have compressed the magnetosphere, exaggerating its asymmetry. Which leads to a difficult question. Are we seeing Uranus' true magnetic field? Or a temporary distortion created by both the planet and its environment? Modern simulations now suggest a more cautious interpretation. The field might not be as chaotic as it looks. It could be highly dynamic, yes, but still stable over long time scales. We just caught it in a single moment. And that brings everything into focus. We are studying a planet with a 6-hour observation window, a magnetic field captured under unusual solar conditions, and decades of theory built on that single moment. And when you step back, one pattern becomes hard to ignore. We are not really observing Uranus. We are inferring it. When you look at Uranus from the outside, something strange becomes obvious pretty quickly. The chaos doesn't stop at the planet itself. It continues, all the way into its moons. Uranus now has over 20 confirmed moons, and that number keeps growing as observations improve. But the real story isn't how many there are. It's how they feel as a system. Because if you look at Jupiter's moons, you see order. Like a miniature solar system with clean layers and stable structure. Uranus is nothing like that. It feels more like a toolbox that got dropped on the floor, and then loosely put back together. Start with the 5 largest moons: Titania, Oberon, Ariel, Umbriel, and Miranda. Titania and Oberon are ancient-looking worlds, heavily cratered, like they've been frozen in time. Umbriel is almost unsettlingly dark, one of the least reflective major moons in the entire solar system. Like a piece of space that refuses to reflect light back. Ariel goes in the opposite direction. It looks younger, resurfaced, reshaped, like something that was geologically active not too long ago. Put them together, and it's almost like 4 different eras of planetary history sitting in the same room. But the one that really confuses scientists is Miranda. It's small, only about 470 kilometers across. Barely a major moon by planetary standards. and yet its surface looks completely over the top. We're talking cliffs nearly 20 kilometers high. On an object that's small, that's almost not supposed to happen. And then there are regions that look completely different from each other, like someone stitched together pieces from entirely separate worlds. One researcher once described it bluntly: it looks like a broken object reassembled in patches. So the question becomes unavoidable: how did it form? One idea is tidal heating, Uranus slowly pulling and flexing its moons from the inside, reshaping them over time. But there's a problem. Uranus doesn't generate strong tidal forces compared to systems like Jupiter. So that explanation struggles to carry Miranda's extreme geology on its own. That's why another, more dramatic idea appeared: repeated destruction and reassembly. Not one formation event, but a history of breaking apart, partially reforming, and breaking again. A kind of long, messy reconstruction process. If that's true, then the Uranian moon system isn't a calm evolutionary family at all. It's more like a debris record of repeated disruption and rebuilding. Some orbital simulations even suggest that in the early solar system, the moons may have been unstable, swapping orbits, colliding, and briefly reorganizing before settling into today's arrangement. But the story doesn't stop there. Because once you move your attention away from the moons, another structure appears: the rings. And they are strange in a completely different way. Uranus rings are not bright or dramatic like Saturn's. They are dark, thin, and extremely precise, almost like lines drawn with intention. We've confirmed more than 10 main rings. Most are incredibly narrow, some only kilometers wide. They're made of dark ice and dust, with very low reflectivity, almost invisible in normal light. And here's the interesting part: they weren't even directly seen at first. They were discovered in 1977, accidentally, during a stellar occultation experiment watching a star blink behind the planet. In other words, they didn't announce themselves. We had to catch them by chance. Compared to Saturn's dramatic display, Uranus rings feel almost secretive. Less like decoration, more like a hidden orbital mechanism. But that raises a serious question. Why are they so clean and narrow? One idea is that they are the remnants of destroyed moons broken apart by impacts or gravitational stress. Another is that they are long-term debris slowly shaped into thin, confined structures by gravity. But both ideas hit the same problem: why don't they spread out? They don't behave like chaotic debris fields. They don't behave like random dust clouds either. They behave like something that is being held in place. And that creates a strange contrast. The moons look like chaos and reconstruction, broken history, stitched together. The rings look like precision, tight, controlled, almost engineered. Inside the same planetary system, you get both destruction and order at the same time. And that makes Uranus feel less like a single story, and more like a layered archive. A system shaped by repeated impacts, rearrangements, and slow stabilization over time. As the saying goes, nothing is ever as simple as it first appears. And with Uranus, that couldn't be more true. When you put all the clues together, something strange starts to emerge. Our understanding of Uranus hasn't really been a smooth process of getting clearer. It feels more like trying to reconstruct an entire image from a handful of scattered puzzle pieces. And the real issue isn't one single mistake. It's that the data itself is just too thin. Let's recap what we actually know and what feels off. First, the observation window. Voyager 2's flyby in 1986 lasted about 6 hours. In planetary science terms, that's basically like taking a single photo while driving past a city, and then writing the entire history of that city from it. Next, the magnetic field. It's tilted about 59 degrees, badly misaligned with the planet's rotation, and even offset from the center. It looks like a system that's been bent out of shape. Then there's the heat problem. Uranus is thought to emit almost no internal heat, while Neptune, its near twin, radiates clearly. Two similar worlds. Two completely different energy signatures. That's hard to reconcile. And then the moons. From Miranda's fractured terrain, to wildly different surface ages, to complex orbital patterns, nothing feels like a smooth evolutionary system. It feels more like something rebuilt, multiple times. Now here's the key point. Individually, each of these puzzles can be explained. But put them together, and they stop fitting. They don't form a coherent picture. It's like combining four datasets from completely different worlds and forcing them into one story. So a bigger question appears. Are we relying too heavily on snapshot science? Because in reality, we can't continuously observe outer planets. Most of what we know comes from single moments in time. In other words, space is giving us screenshots, not full videos. But what if those screenshots are misleading? Solar wind spikes, compressed magnetospheres, extreme seasonal conditions. Any of these could distort what we see, meaning the state we observe might not be the average at all. It could be an extreme moment. That leads to an uncomfortable possibility. A lot of what we think we know about Uranus may be based on a special case, not a typical one. So the question becomes sharper. Are we actually describing Uranus, or just describing the moment we happen to catch it? And then the problem escalates. If 6 hours of data can shape decades of theory, are we studying the planet itself, or just the limitations of our observation? This connects directly to a more modern shift. With instruments like the James Webb Space Telescope, the picture is starting to change. We're finally seeing deeper layers, subtle atmospheric activity in infrared, cloud structures that evolve slowly over time, local storm systems that don't disappear, they just hide in ways we couldn't detect before. And even more interesting, the relationship between the rings and the atmosphere looks more dynamic than expected. The rings aren't perfectly static. They may be influenced by small gravitational disturbances. And some tiny moons, previously uncertain or overlooked, are being confirmed again. Their orbits might be slowly reshaping the ring system itself. All of this points to a shift in perspective. Uranus may not be a frozen blue sphere at all. It might be an extremely slow-moving dynamic system. Change isn't absent. It's just so slow that we mistake it for stillness. As the saying goes, still waters run deep. This changes everything. Older models treated Uranus as a static object, a structure that simply is what it is. But newer thinking is moving toward dynamic systems. Things evolve. We just don't see the full timeline. And that's a major turning point, not just for Uranus, but for how we understand outer planets in general. Which leads to the final question. If our past understanding is built on a brief flyby, and our future observations are still limited in scale, are we constantly using local snapshots to explain global systems? And this isn't just about Uranus. It's really asking something bigger. When we can only see a small slice of cosmic time, can we ever truly understand its long-term behavior? When you piece everything back together, a strange pattern starts to appear. At first, it feels like we've been studying Uranus itself. But by the end, the question quietly shifts. Maybe what we've really been studying is not the planet at all. It's how we look at it. So we go back to the original question. Why have we misunderstood it for so long? Is it because it's too far away? Too cold? Too strange? Those answers sound reasonable, but they don't go deep enough. The real issue might be much simpler and more uncomfortable. We only have a very short observation window. In 1986, Voyager 2 flew past Uranus in about 6 hours. In cosmic terms, that's barely a blink. But human science often tries to build long-term theories from these brief moments. And that creates a fundamental limitation. It's not that Uranus is special. It's that our method is inherently constrained. Planetary science is, in a sense, time imbalanced. We can't park spacecraft around every planet for centuries. We can't wait for full seasonal cycles before drawing conclusions. We pass by, we observe, and we record. It's like trying to understand a full movie from a single photograph. And here's the important part, this isn't unique to Uranus. Jupiter, Saturn, Neptune, we've all only seen snapshots of them too. Some worlds just change quickly. Others change so slowly that we assume they don't change at all. And that leads to a deeper question. What does it even mean to understand a planet? Is it knowing its structure, its state at one moment, or its behavior over time? If it's the last one, things get difficult very fast, because we almost never have full time series data for planetary systems. We see fragments, not continuous stories. So a scientific question slowly turns into a methodological one. Are we over-relying on snapshots to explain long-term systems? If so, the error isn't small or local. It becomes structural. And at that point, a reversal starts to make sense. Maybe Uranus isn't an anomaly. Maybe it's just a magnifier of our observational limits. It shows us something uncomfortable. Not every system can be understood through short-term data, but right now, that's almost all we have. In that sense, Uranus may not be a special case at all. It might be a warning sign, a reminder that the universe wasn't designed for instant observation, but our tools are optimized for exactly that. And there's always tension between the two. So the question moves one final step deeper. If we send another mission to Uranus, we'll get more data, more detail, better resolution, clearer magnetic maps, more atmospheric structure, maybe even a better understanding of its rings. But the real question is this: will we just turn another moment in time into another truth? Because if the way we observe doesn't change, then what we collect will always be the same thing: new snapshots, not a continuous reality. And so the question is no longer just about Uranus, or even about any single planet. It becomes something quieter and more unsettling. When we can only see a small slice of cosmic time, are we truly understanding the universe? Or are we just endlessly correcting the edges of our own blind spots?
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.